Welcome to the Practical Order and Inventory Management Logic with the Python and AWS course. In this course, we will implement the robust business logic on AWS services while acquiring essential domain knowledge regarding order placement, receiving, and inventory control. This course consists of 6 sections. First, in Section 1, I will introduce the course objective and the overall system architecture. Next, from Section 2 through Section 4, we will dive into the code and implement a specific business logic for each process. In Section 5, we will integrate all these components to verify the system flow. Finally, in Section 6, we will wrap up with a summary and introduce some advanced features for further development. Let's begin Section 1, Introduction and the System Design. In this section, we will outline the course objective and the learning roadmap. We will also discuss the essential domain knowledge, specifically why inventory management is necessary, and finally, we will proceed with the AWS environment setup, including account creation. Here are the objectives of this course. First, you will understand the essential logic required for inventory management, such as available inventory and reorder points. We won't just write code, we will understand the underlying domain knowledge together. Next, you will write Python code using classes on AWS Lambda. Programming doesn't end with development. You need to write maintainable code considering future operations. In actual system development, we execute unit tests after developing each function, followed by integration tests to combine all features. In this course, you will experience this real-world development approach through hands-on practice. Finally, you will be able to build APIs using key serverless services, API Gateway, Lambda, and DynamoDB. The goal is not just to use AWS, but to understand the business operations and build a high-quality system. Next, let's look at the overall architecture of the system we will build in this course. The logical inventory logic calculates the number of items physically present in the warehouse. The available inventory logic calculates the difference between logical inventory and allocated inventory. The order allocation logic is executed to reserve stock the moment an order is received from a customer. The outbound shipping logic is executed when goods are actually shipped from the warehouse. The inbound receiving logic is executed when goods arrive at the warehouse from a supplier. The safety stock logic calculates the minimum inventory required to prevent stockouts. Finally, the reorder point logic calculates the threshold for when to place a new order. We will create these logic components using Python functions. Here is the flow of the course. We won't write and run all the code at once. Instead, we will develop each function and improve quality step by step. In a real-world development environment, multiple functions are developed in parallel, often by different developers. First, in sections 2 through 4, we will perform unit testing. Next, in section 5, we will integrate the individual functions and test the end-to-step flow. In unit testing, we will implement the calculation logic such as inbound logic and order allocation logic one by one in Python. We will verify if each component works correctly using the test features of AWS Lambda. After ensuring quality with unit test, we will connect these functions with API Gateway and DynamoDB to perform integration testing. In integration testing, we will test the entire system against real business scenarios, such as if I hit the inbound API, does the database stock increase? Or if I hit the order API, does the available inventory decrease? For your reference, in general enterprise system development, we define the scope and the requirements based on actual business needs. In the requirements definition phase, we concrete with the business requirements for the system, then move to the design and development phases. Developed functions undergo unit tests and integration tests to verify quality incrementally. Finally, the system is accepted by the user and moves to the operations phase. In practice, this involves collaborative work among multiple parties, such as consulting firms, system integrators, and client companies. This is the overview of the AWS services we will ultimately build in this course. The configuration of API Gateway, Lambda, and DynamoDB is a classic modern serverless architecture. Let me briefly explain each role. First, API Gateway acts as the system's front door, accepting requests from the outside. And next, AWS Lambda executes the system processing. This is where your Python logic runs. Finally, DynamoDB is the database that stores the current inventory counts. Lambda reads the current stock from DynamoDB, performs calculations, and writes the results back. We will make this entire flow callable via API Gateway. The serverless architecture is a convenient configuration where you don't need to worry about server OS management or scaling. Next, I will introduce essential domain knowledge. Why is inventory management necessary? The goal of inventory management is to deliver the right product at the right time in the right quantity to the customer. Neglecting proper inventory management will negatively impact finances and the business. In inventory management, we need to maintain an appropriate inventory level, neither too much nor too little. If inventory is too low, stockouts occur. This leads to opportunity loss, meaning we lose sales we could have gained. In the long term, it gives the impression that this shop is always out of stock, causing a loss of trust. On the other hand, if inventory is excessive, cash flow gets worse. Inventory is essentially a cash in a different form. If you have too much unsold stock, your cash stops circulating. Additionally, warehouse storage fees, insurance, and management costs increase. Depending on the item, products may get old or expire, leading to disposal and confirmed financial loss. We need to control the trade-off between stockouts and excess inventory, optimally using systems and logic. Now, let's look at the flow of order management and inventory control. First, our company is in the center. We currently hold some stock of a product. On the left are customers from whom we receive orders. On the other hand, when stock runs low, we place orders with the manufacturer. Suppose we receive a sales order for 3 items from a customer. Currently, we have 15 items in stock. We allocated 3 items. Physically, there are 15 items in the warehouse, but since 3 are allocated to Company X, the unallocated available inventory is only 12. Next, we ship the 3 items. At the same time, we record the sales. I am simplifying the explanation here, but strictly speaking, we must consider lead time due to the physical distance from the warehouse to Company X. Also, processes like inspection and acceptance are performed before information is transmitted from Company X's system to our system to record the sale. When the goods are shipped, inventory decreases by 3 at this point. We register this decrease in the system and reduce the logical inventory. Next, we receive another sales order for 4 units of product A from the same customer. After the previous process is finished, we currently have 12 items in stock. Using the same process as before, we allocate 4 items. Since 4 are allocated, the unallocated available inventory becomes 8. As before, we ship the 4 items. The logical inventory now becomes 8. Here, we introduce the concept of safety stock. Safety stock is the minimum inventory kept to prevent stockouts against uncertainties like sudden demand spikes or lead time delays. For example, suppose we set the safety stock for product A to 10. Since we only have 8, we are short by 2. Therefore, we place an order for 2 items with manufacturer Y. Manufacturer Y produces and delivers 2 items to us, and we process the inbound of product A into the warehouse and register it in the system. As a result, the current inventory becomes 10. The flow up to this point represents the basic logic of order and inventory management. Simply put, outbound decreases stock and inbound increases stock. Therefore, the formula current inventory equals previous inventory plus inbound minus outbound holds true. This is the most fundamental logic of inventory management. As explained at the beginning, in this course, we will divide this flow into 7 parts and create the logic for each. There are dependencies among these 7 functions. First, we will develop each as a Python function, and finally, we will integrate them to test along the actual business flow. In integration testing, we will prepare scenarios following the business flow and test using sample data. Next is the hands-on session. First, we will set up the AWS environment. As mentioned at the beginning, we will develop this system using AWS services. First, we will create a DynamoDB table to store and update current inventory counts in real time. Let me briefly introduce DynamoDB. DynamoDB is a fully managed key-value database. It is one of the most representative database services in AWS and is widely used in the industry. DynamoDB stores data as keys and values. Because key-value databases have a simple structure with the paired keys and values, they have the advantage of faster processing compared to general relational databases. DynamoDB has keys and attributes. There are 2 types of keys, partition key and sort key. The partition key acts like a primary key. Internally, data is distributed based on the partition key, enabling efficient processing. The sort key is used to sort items within that partition. Next, DynamoDB has a concept called capacity modes. There are 2 pricing modes for table reads and writes, on-demand and provisioned. On-demand means the cost fluctuates based on demand. In other words, if usage increases, the cost increases accordingly. Provisioned reserves a specific usage amount at a fixed price. This means the cost remains constant regardless of whether usage is high or low. You use provisioned capacity mode when capacity can be predicted in advance, and on-demand mode when capacity cannot be predicted. I have prepared a comparison table here. You don't need to memorize the detailed numbers, but please note that you can select the lead performance settings for each. This is the product stock table we will create in this course. We will set product_ID, a unique string, as the partition key. The other items are set as attributes. Item name is defined as a string, while other items like inventory counts and the lead times are defined as numbers. This is a step to create a root account and IAM user. First, create a new AWS account and then set up IAM user. IAM is a service that manages permission of users in AWS. First, search AWS in your browser and go to the AWS web page. You will see a button in the upper right corner that says Sign into the console and click it. If you already have an account, you can sign in from this page. To create a new account, click Create a new AWS account. Enter your email address to authenticate your email. A verification email will then be sent to that email address. Next, enter your personal information such as address, credit card, phone number, etc. A credit card or debit card is required for your billing even if your billing is zero. If you are not belong to a corporation and use AWS for personal development or just learning, I recommend you to choose the basic plan, which is free of charge. For developer plan and the business plan, you can get support from AWS customer engineers. Once you have completed this process, AWS account will be created successfully. This is a page called Management Console, and this will be the main page when you use the AWS resources from now on. Now, I'm going to configure IAM. The first account that created is called a root user, and it will be a powerful account like administrator with access to your credit card. If the account is compromised, there is a security risk. Therefore, AWS recommends that you create an IAM user and sign in as an IAM user instead of using a root user normally. First, type IAM in the search window above and move to IAM's dashboard. This is the IAM dashboard. In the initial state, root user has MFA is marked with a red triangle. It is recommended that you install the token apps on your smart device, and next time you sign in as a root user, authenticate with MFA. Next, create an IAM user. The next time you sign in as usual, sign in as this IAM user. You should not sign in as the root user except when checking your credit account. Click on User in the left menu, then Add User. Set the username. Check the access key and the password field for the credential type. The access key is used for the API, CLI, and SDK, and the password is used to sign in to the Management Console. Select Attach Existing Policies directly and choose Administrator Access. This will give the IAM user all privileges except credit card access. The tags can be any text you like. Tags allow identification of IAM users. If you create multiple users in the future, you may set the tags to identify each user. After successfully creating a user, be sure to save the access key and the passwords that are displayed. You can also download this in CSV format. When you have done set up IAM, you will return to the console again, and I will briefly introduce you to the structure of the screen. From the menu bar above, you can move to the various management screens. You can return to the top page by clicking AWS logo on your left. Click on Services to see all the services offered by AWS by category. You can also register frequently used services as favorites. Click on the CLI logo to open CrowdShell. By doing so, you can manage the command line from within your browser as well. Click on the bell mark to view various notifications. You can find out about events, changes, and incidents for the services you are operating. Click on the question logo to get support. The type of support available depends on the plan. For example, the basic plan allows ticket-based questions about fees, while technical support is available with paid plans. By clicking on the gear-shaped logo, you can edit the language, the visual mode, and so on. This is a recently added feature. The menu bar configuration may change in the future. Next, click on the pull down where the region name is listed to navigate to the AWS region. Northern Virginia is selected by default. Basically, by selecting a region that is close to where you want to deploy your services, you can access your resources with low latency. Also, the services deployed and the fees vary slightly by region. Since AWS is a US company, so releases are generally the earliest in the US region and are then after rolled out to other regions. Documentation and other information is also available in English for the latest services and is gradually being translated into other languages. Finally, you can check the account information you have created from the upper right corner of the console screen. Clicking on an organization will take you to the AWS Organization Service page, where you can view information about the organization you belong to. From here, you can also check your service quota and usage status and so on. If you need to access credit information, you will need to sign out of your IAM user and sign in as the root user. So now let's create the DynamoDB table. Currently, I am at the top of the AWS Management Console, and if you type the DynamoDB on the top search bar, clicking on the DynamoDB icon, and it will navigate to the DynamoDB service page. And you will likely see the dashboard initially, and clicking on the Create Table from the side menu on the main screen to start to create a new table. So from the table name, enter the product stock this time, and next sets the partitions key, and name it the product underscore ID, and sets the type to the string, and leave the sort key settings empty. And we will use the default setting this time, and we select the on-demand capacity mode, and scrolling down to the bottom and click on the Create a Table. So the table is now being created as a status, and it usually takes a few seconds to a few tens of seconds after the clicking on the button for the status to turn active. So once the table is ready, and go into the product stock table, and we will now insert the initial test data, where you can use the command line to input the data. But for this hands-on lab, we will input the data directly via the console screen. So inside the product stock, we will create an item, and clicking on the Explorer, the item, and then clicking on the Create Item. So for the existing partition key, the product ID, enter the A001, and which representing the product ID. Next, we will add the attribute one by one. The first, the new string, and named it the item name. For the value, enter the sample product A. Next, add the new attribute, select the number, and name it the logical underscore and stock, enter 100 as the initial value. And this represents that we have 100 units of the logical inventory. Similarly, add the new number and add the name with the reserved stock, and this represents the allocated inventory and sets the initial value to 0. Next, add another number value and names the average AVZ daily demand, and this representing the average daily shipment demand. And we will discuss the detail in later chapter. And for now, and set this to 10, 1, 0. And next add the new attribute with a number named the read time date, read underscore time underscore date, and this represents the read time from the pressing order to receiving it, and set this to the 5, and we will also explain in the later chapter. And finally, add the number and the safety date, and this representing the number of the days worth of the stock we keep as the safety stock, and set this to the 3. And once you have entered the order field, clicking on the create an items. So now the item has been created, and please verify that the item, the A001 we just created, is displayed at the bottom of the list. And this completes the creation of the DynamoDB table. And finally, there is one important note regarding the region. And please ensure that we will have the Lambda function, the API gateway, and the DynamoDB table, and we create later are all in the same region. I will consistently use the US, the East North Virginia, the US East 1 region throughout this code. And if you switch the region resources will not show, for example, I'm going to choose the Ohio, and the resource will disappear, will not show up because they are the region specific. For example, the DynamoDB table we just created will appear here, and if you change the region from the Ohio to North Virginia, and switch back to the North Virginia, so the product stock appears again. The API gateway, Lambda, and the DynamoDBs are all the region-specific resources, so please make sure to store everything within a single region. Next, we will proceed to Section 2, implementing inventory movement logic. In this section, as our first business logic, we will develop the logic to calculate the changes in logical inventory using Python. The developed Python code will be deployed to AWS Lambda. But first, let me introduce the concept of logical inventory. As introduced in the previous section, the current inventory is processed using the calculation previous inventory plus inbound minus outbound. And this is the basic concept, but in reality, the timing of inbound and outbound does not necessarily happen at the same time. Therefore, to maintain inventory integrity, we need to consider the timing of these processes. First, let's look at the inbound flow. Inbound refers to the process where goods arrive at the warehouse from suppliers or factories and are formally recorded as inventory. In actual logistics flows, goods are transported by truck and we perform an inspection. If there are no issues, we proceed with put away, placing items on warehouse shelves. At this time, we also update the system. In practice, scanning the barcode labels attached to the products with a handheld terminal automatically updates the system. To reiterate, when inbound processing is performed, we increase the inventory by that amount. Next is outbound. Outbound refers to the process where goods formally leave the warehouse based on customer orders. Based on the order details, we perform picking from the warehouse shelves according to instructions such as the shipping destination, item name, and delivery date. We then inspect and pack the products and create a shipping label. When outbound is performed, we decrease the inventory by that amount. Here, I would like to introduce stock taking or physical inventory count. Although we will not cover it in this course, the actual physical inventory and the system inventory may differ. Periodically checking this discrepancy allows for verification of inventory status and accurate financial management. The General Warehouse Management Systems, WMS, they typically have features to reflect the stock-taking results to reconcile system inventory with the physical inventory. Ultimately, the results of stock-taking are reflected in the accounting system. Next, let's move on to the Python implementation. First, let me introduce Python classes. A class is like a blueprint that bundles data and logic together. By doing this, we can group data with the operation performed on that data, preventing unintended external changes and maintaining data integrity. Strictly speaking, this is a fundamental principle of object-oriented programming. But since the focus of this course is on the inventory management flow, I will skip the deep details. However, using classes improves code readability and maintainability, so we will utilize Python classes in this course. In this section, we will use a class named Inventory Manager. Inventory Manager encapsulates the current inventory count and the inventory movement logic. This organizes code with the similar functionality, making it easier to test and reuse. I apologize if the text is a bit small, but let me introduce the actual code we will create. First, we create the skeleton of an inventory manager. The part written as init is called the initialization method or constructor. This is the part that is executed first when the class is called. As a side note, in Python, functions are defined using def. Also, creating concrete data by calling a class is called instantiation. An instance means an actual entity. Self refers to this class instance itself. The code self.logical underscore stock equals logical underscore stock means save the logical underscore stock passed from the outside argument as my own self-logical underscore stock. With this, the class can now remember what the current inventory count is. Next is the inbound method. Since this corresponds to logic 5 in the diagram shown at the beginning, I have labeled it as logic 5. We will add a method named receiveStock. Inbound processing increases the inventory. We define the receiveStock method, making sure not to forget self. In the validation step, we first reject impossible requests where the inbound quantity is 0 or less. If the quantity is 0 or less, we return false and an error message. The core logic is self.logical stock plus equals quantity. This is the heart of the inbound calculation. We add the inbound quantity to the logical stock that the class itself remembers. Finally, we return true and a success message. Returning this success or failure status and the message is useful for subsequent processing. Next is the outbound method. We define a method named shipOrder. The shipOrder method is defined similarly to receiveStock. However, unlike inbound processing, the core logic for outbound processing includes a specific business logic. Is there enough inventory? We use if quantity greater than self.logical stock to check if the requested shipping quantity exceeds the current inventory. If there is a shortage, we return false and stop the process. This prevents the inventory from becoming negative. Only when there is sufficient inventory do we decrease the stock using self.logical stock dash equals quantity. Next, we will deploy the Python code explained earlier to an AWS Lambda function. Before introducing Lambda, let me explain the concept of serverless within cloud computing. First, as a standard classification of cloud services, we have SaaS, PaaS, and IaaS categorized by the layer of service provided. A SaaS, software as a service, is a cloud service that provides software over the internet. A PaaS, A platform as a service is a cloud service that provides platforms such as OS and middleware. IaaS, infrastructure as a service, is a service where you can utilize infrastructure such as servers and networks over the internet. There is a concept called serverless computing, which is analogous to SaaS, PaaS, and IaaS. The original meaning of serverless refers to services that do not require server management. Management tasks such as physical servers, virtual machines, scaling, and maintenance are automated by the cloud provider. In a serverless environment, developers can focus on coding without managing infrastructure like servers. Lambda is an event-driven serverless computing service. Event-driven means the service executes triggered by specific events. It is not always running. Also, you are billed only while the function is executing. Since it is serverless, there is no need for infrastructure layer management. Lambda automatically executes code in response to events while integrating with the various resources. The services that execute function in the cloud are called FaaS, Function as a Service. It supports various programming languages such as Java, Python, and Go. It can integrate with a wide variety of AWS services. Lambda supports a wide range of use cases. For example, it can execute functions triggered by HTTP requests in integration with API Gateway, execute functions triggered by S3 data uploads, or execute functions on a fixed schedule. This is the lifecycle of the Lambda execution environment. Skipping strict technical details, the Lambda function lifecycle consists broadly of init, invoke, and shutdown. In the first invocation, Lambda downloads the code, starts the runtime, and performs initialization. In the next invoke phase, the function runs to process the event. When processing is complete and it remains idle for a certain period, the execution environment is destroyed. Since Lambda is an event-triggered service, it does not run continuously. It launches triggered by specific events such as external triggers or schedulers. By default, the init phase is limited to complete within 10 seconds. If it exceeds 10 seconds, it will be retried. The timeout is a maximum of 15 minutes. When many requests are sent simultaneously, Lambda launches execution environments to perform parallel processing. The number of concurrent executions per region is limited to 1,000 by default. If requests exceed this, an error occurs due to throttling. If the number of requests increases and the function fails to operate due to reaching the Lambda concurrency limit, you need to request a quota increase. According to AWS official documentation, it's possible to raise this limit to tens of thousands. In this system, we are using AWS Lambda, but AWS offers many other computing services. I have summarized the representative ones here. To reiterate, Lambda is a serverless service and does not run continuously. It runs only when there is an event. Also, since you are billed only during execution, it offers excellent cost performance. On the other hand, EC2 is a virtual server service provided by AWS that runs continuously and incurs fixed costs. For our system, the calculation time is a matter of seconds, and the data volume is sufficiently small, so Lambda is the optimal service. Order processing is executed via API each time, and the scale of each calculation is small. In reality, there are systems that calculate inventory once every 24 hours. In systems for large enterprise factories or retail stores, large-scale batch processing is often executed at night. For massive processing where a single runtime exceeds 15 minutes, other services should be considered. Let's start the hands-on with Lambda. Just like the last time, we will create a Lambda function from the AWS console homepage and enter the LAM the Lambda. So, and it will navigate to the Lambda's functions page. So, in the initial state, clicking on the left main bar, and nothing will be listed under the function in the left menu bar. So checking that I am in the North Virginia region, just like earlier, I will proceed to create a new function, clicking on the create function. And we will create the function from here. Then currently, besides the Lambda function from the scratch, the option to use the blueprint or the container image. However, since we will be writing the code ourselves this time and select the author from the scratch. For the function name, I will set to the stock manager lambda, and next we will set the runtime. And since we are using the Python this time, so type pyth. So the latest supported version 3.9 to 3.14 are displayed here. Any of these versions will work fine, but select the latest version, the 3.14. And we will create the function with the default settings for the other parts. But in the permission, there is a setting for the default execution role. By default, they create a new role with the basic Lambda function is selected. And if this is selected, a new permission role will be automatically created. And we will introduce this later, but an IAM role will be automatically created. And we will edit the IAM role in the later section as well. So an IAM role will be created based on the name with the stock manager lambda. And with that, let's click on the create the function. The lambda function, the stock manager lambda, has been successfully created now. And normally it takes from the few seconds to few tens of seconds from clicking the create function until it is actually created. And since it is a serverless service, no servers are launched, and so the service starts up immediately in this manner. So let me explain this menu. There are tabs at the bottom such as the code, test, the monitor, the configuration, the aliases, and the version. And in this hands-on, we will use the code and the test, and we will also use the configuration later. In the code tab, the sample code for displaying the hello world message is currently written, but we will write the actual Python code for the lambda here. And later we will also enter the test event here to execute the unit test. And we will not use the monitor this time, but the invocation of the lambda and the error accounts are displayed here. And in the configuration, and which we will set later, the IAM role displayed here. And clicking on the permission from the left menu bar, you will see that IAM role named the stock manager lambda role is currently set. And from here, we can control the permission in detail. And we will look at this in the later section. So now let's going back to the code tab. And I will copy and paste the code directory here. It is the bit long, but this is the code I explained the lecture for setting out the inbound and outbound logical inventory, the init and the received stock and ship order. And scrolling down to there is a function called the lambda event handler, and which actually retrieve the events from the outside and process them. And since this is for the unit test in the section 2, It is designed not to interact with the external services like a DynamoDB or API gateway yet. It is designed to input data in JSON format directly for the unit test and manually check the result later. So scrolling down to the status code, the status code is set to return the 200 for the success and 400 for failure. So with this state, the clicking on the deploy and the deployment should also complete immediately. Now that the Lambda function is deployed, we will proceed to execute the unit test. Here is the overview of the unit testing plan. In this unit test, we will define and execute tests for 3 scenarios: inbound, outbound success, and outbound failure. For inbound, we use sample data where the current inventory is 100 and the inbound quantity is 50. As the test result, we expect the inventory to be updated to 150. For the outbound success case, we use sample data with a current inventory of 100 and an outbound quantity of 20. We expect the inventory to become 80. Finally, for the outbound failure case, we use sample data with a current inventory of 100 and the outbound quantity of 200. Since the outbound quantity exceeds the available inventory, we expect to display an insufficient inventory error. So now let's go back to the Lambda's page and again actually execute the unit test from here. So clicking on the test tab, and from here we can define the test event and execute the test. First, we will execute a test where we receive the 50 items into the current inventory of 100. I will name the event as the test receive, and which means inbound. Leave the invocation type as the synchronous and event sharing setting as the private, because we are not sharing this externally. And scrolling down, and there is a place to actually input test data and copy and paste the test data in JSON format here. The action is receive, which means inbound. The current stock is 100, meaning there are 100 items currently in stock. And the QTY, the quantity is 50, and meaning we are receiving 15 items. So now let's execute the test. First, once save, and clicking on the test. So since the processing is very simple, the test should execute immediately. So the results related to the processing contents are displayed here. At the top, you see the status code equal to the 200, and this indicates the success 200 OK. And there is a complex string written here, but this is the string format that the DynamoDB or API gateway will actually exchange within the system in later chapter. For string indicates a human reading, look at the log output section below. Here, it says the inbound success, and the current logical stock is the 150. And since we received 50 items against the initial stock of the 100, the current logical inventory is 150 as expected. And this confirms that the test was successful. On the same way, next let's execute another test in the same way. So scrolling down and clicking on the create new event, and I'm going to name the event name to the test the ship success, meaning the outbound success button. And I'm going to copy and paste the JSON format in the same way. In the JSON format, the action is zip, meaning the outbound, and the current stock is 100 and the QTY is 20, and clicking on the save and execute the test. Okay, and on the same way, the execution results should appear immediately. Looking at the log output, so the original logical inventory was 100, and we shipped the 20, so the current logical inventory is 80. This is also behaving as expected. So finally, let's create one more new event. Clicking on the create a new event, and the name it this time test ship fail stock out, represents the stock shortage pattern. And scrolling down, copy and paste the JSON code. So similarly, the action is ship and meaning outbound, and the current stock is 100, and we try to ship the 200 item. The logic should result in the stock shortage. Clicking on the save and clicking on the test. So the execution finishes immediately. In the output, you can see the error message saying the shipping failed, insufficient stock. So with this, we have completed all the three types of the test, and this concludes the explanation for the section 2. Next, we move on to section 3, implementing order and allocation logic. In this section, we will first introduce available inventory as essential domain knowledge. Then, we will extend the Python code developed in the previous section and deploy it to Lambda. In the previous section, we implemented the physical movements of inventory, inbound and outbound. However, in reality, there is a time lag between the moment an order is received and when it is shipped. In system management, we must account for this time lag. Let me explain the concept of allocation using a simple example. First, assume there are 100 items in the warehouse as of 9 a.m. Shipments via truck are scheduled for 3 p.m. At 10 o'clock, we receive an order for 70 items from a customer. Since there are 100 items in stock, we can meet the evening shipment. At 11 o'clock, another order for 50 items comes in. At this point, since the system still sees 100 items, it incorrectly judges that shipment is possible. However, in reality, a shortage of 20 items has occurred. Logical inventory decreases at the timing of outbound. However, orders occur before outbound. If we rely only on logical inventory, we end up double counting stocks that is already committed as if it were still available for sale. To solve this problem, we use the concept of allocation to manage inventory in two states. Here, we will use allocated inventory and available inventory. Allocated inventory refers to stock that has been ordered but not yet shipped. Available inventory refers to stock that is truly available to be sold right now at this moment. Applying this to the previous example, at 10 o'clock, allocated inventory is 70 and available inventory is 30. For the 11 o'clock order, since there are only 30 items in available inventory, the allocation fails. Available inventory is not stored in the system database, but is derived via calculation. The formula is available inventory equals logical inventory minus allocated inventory. This is the order allocation logic. The system executes this logic the moment an order is received from a customer. If the order quantity is greater than the available inventory, it returns an error and rejects the order. If the order quantity is smaller than or equal to the available inventory, the order succeeds. Simultaneously, we update the database to increase the allocated inventory. Note that we do not reduce the logical inventory at this stage. By increasing the allocated inventory, the available inventory will automatically decrease based on the calculation. In the next chapter, we will implement this new logic by adding it to the Inventory Manager class. Next, we will extend the Python code to add the available inventory logic. In this section, we will adapt the Inventory Manager class to support allocation logic. We will extend the class created in the previous section to implement the concepts of reserved inventory and available inventory into the Python code. Specifically, we will add a reserved stock allocated inventory to the initialization method, and we'll add a property to calculate available stock. Add a new method called the reserve order. Modify the existing ship order method to support allocation. First, we modify the initialization method so that Inventory Manager can remember not just logical inventory, but also reserved inventory. We add the reserved stock to the arguments of init. We add the line self, the reserved stock equals the reserved stock, so the class itself can store how many items are currently reserved. For your reference, the receiver stock method does not involve allocation, so no changes are needed there at this point. Next, we implement logic number 2. Available inventory equals logical inventory minus reserved inventory. Since this state is derived via calculation, it is a standard practice in Python to implement it as a property rather than a method. By adding the AT-property decorator, you can call the available stock function like a variable, such as stock.availablestock. The content is exactly the formula we learned, self.logicalstock minus self.reservedstock. If the class's logical stock or reserved stock changes, the value returned by this property will automatically change. Next, we add the order allocation method, logic number 3, which is the core of this section. First, the stock check. We add if quantity greater than self.availablestock. In the ship order method created in the previous section, we compared against self-logical stock, but in the reserve order, we compare against the self-available stock we just implemented. Next is the allocation process. We add self.reserved stock plus equals quantity. If the stock is sufficient, we do not change the logical stock. Since goods have not physically moved from the warehouse yet, the logical inventory remains unchanged. Instead, we increase the reserved stock. By doing this, the mechanism ensures that the available stock automatically decreases based on the calculation. Next, we modify the ship order method. Implementing allocation requires updates to the ship order logic created in the previous section. Outbound processing now changes to shipping stock that has already been reserved. Previously, ship order reduced logical inventory directly. Now, we ship what is reserved. In the stock check, we change the check target from logical stocks to reserved stock. We also modify the stock reduction process. Self, logical stock minus equals quantity represents the physical reduction of goods from the warehouse. We add self.reserved stock minus equals quantity to represent that the reserved stock has been consumed. When ship order is called, both inventories decrease simultaneously. This is the correct logic that covers the code changes. In the next lecture, we will verify if this logic works correctly using unit tests. Next, we will deploy the Python code to AWS Lambda and execute the unit tests. First, let me outline the unit test plan for this section. We will define 3 scenarios. one allocation success case and two allocation failure patterns. The first, in the allocation success case, the current logical inventory is 100 and the reserved inventory is 0, meaning the available inventory is 100. We receive an order for 30. As a result of the calculation, logical inventory remains 100, the reserved inventory becomes 30, and the available inventory becomes 70. Next, in the first allocation failure case, the available inventory is 100, logical 100, reserved 0. We receive an order for 101. Since the order quantity exceeds the available inventory, an error is returned along with an order rejected message. And finally, in the second allocation failure case, the current logical inventory is 100 and the reserved inventory is 70, meaning the available inventory is 30. We receive an order for 40. Since the order quantity exceeds the available inventory, an error is returned along with an order rejected message, and meanwhile the available inventory state is updated. The third case might be a bit confusing, so let me explain it using a formula. In the initial state, logical inventory is 100 and the reserved inventory is 70. Based on these, the available inventory is calculated as 100 minus 70 equals 30. However, since the order is rejected, the reserved inventory does not change and maintains the status quo. In other words, this means only the available inventory calculation logic was processed, but the order allocation logic was not executed. So, continuing from the previous section, and we will deploy the code to the Lambda function named the stock manager Lambda and execute the test. So using the same operation as before, open the code tab and input the Python code directly here, and I will copy and paste it as is. So inside here, okay, you will find the inventory manager class explained in the lecture, and this is the version we update in the section 3. And we have added a new variable, the reserved stock, and alongside the logical stock. As I explained earlier, the calculation for the available stock and the received stock and the received order are written here, and scrolling down to the bit to the Lambda handler function. The function receives the event from the outside and executes the process. And we have modified the function access the current logical stock and the current reserved stock from the outside, the meaning the current logical inventory and the current allocated inventory are passed in. In reality, outside refers to the receiving data from the API gateway and the DynamoDB. But for now, we will input using the JSON test data. So clicking on and deploy, and deployment should complete immediately. So now let's go to clicking on the test tab. So let's execute the test. And using the same procedure as before, create a new event. And first, let's look at the case where the allocation succeeds. And I'll name it the test, the reserved success, and paste the JSON with this. Okay, you can see the number of the argument has increased compared to before, and we now have the current reserved stock displayed here in addition to the current logical stock. And behind the scene, the system corrects the available stock, the available inventory, by subtracting the the reserved stock from the logical stock. And in this case, it calculates the 100 available items. Since we are allocating the 30 item, the test should succeed. So going up and clicking on the save and execute the test. Okay, so looking at the log output, you can see the order was successful, and okay, the stock has decreased from the 100 by 30 and becoming the 70, and the reserved stock has become the 30. And however, the logical stock is remain at 100 because the physical inventory doesn't change at this stage, and this is the expected result. So continuing on, let's create another new test event. So scrolling down to the clicking on the create a new event and new test event, and look at the case where the allocation failed. So I'll name the test resolved fail simple. Okay, scrolling down and copy and paste the event, the JSON. Okay, this time we have the logical inventory, logical stock equals 100, and we will attempt to allocate the 101 items by subtracting the allocated stock from the logical stock. The available inventory is 100. Attempting to allocate the 101 item should result in the error. So clicking on the save and test. Okay, and scrolling down to the log output. So the result should appear immediately, and since the available inventory is 100 and the order is for the this time 101, and the message is order failed, insufficient stock is displayed. So finally, let's try one more pattern. Create a new event, and event names the test resolved failed complex, and paste the JSON, and copy and paste the JSON here. So for this case, the current logical stock is 100, and the current reserved stock is 70, and we attempt to allocate the 40 items. In other words, the logical stock minus reserved stock gives them the available stock of the 30. Since we are trying to allocate the 40 items against this state, it will be fail, and the calculation itself is performed, but the allocation failed. So going up and clicking on save and execute the test. Okay, the calculation result returned immediately. So here the available inventory is 30, and since the order request is the 40, and the order failed, insufficient stock is returned. So all test cases have produced the expected result, and this concludes the unit test for the section. Next, we move on to section 4, implementing reorder point logic. Again, we will first introduce the reorder point logic as essential domain knowledge. Then we will extend the Python code developed in the previous sections and deploy it to Lambda. In the opening slides, I explained that we place an order when inventory drops below the safety stock. However, in reality, we must place orders taking procurement lead time into consideration. Let's look at this flow in more detail. Let's look at the flow from ordering to inbound. It takes time from the moment an order is placed until the goods arrive at the warehouse. This is called procurement lead time. The process involves executing the order from the system, the supplier preparing and shipping the goods, truck transportation, arrival at the warehouse, and finally inspection and put away. If you place an order only after the stock hits zero, you will have a stockout during this entire period. Therefore, you must place an order before the stock equivalent to the lead time runs out. Also, even if we account for procurement lead time, unexpected events can occur, such as sudden demand spikes, production troubles at the factory, or delivery delays due to bad weather. To prepare for such a situation, the buffer kept separately from the inventory used for normal consumption is called the safety stock. A safety stock allows us to prevent a stockout even if there are some fluctuations. As a side note, calculating safety stock is difficult and perfect prediction is impossible. I personally worked in supply chain management at an automotive manufacturer. Aside from traffic accidents and bad weather, many unpredictable events occur, such as customs accidents and political risks. These unforeseen events cannot always be handled by the system and often require manual intervention. While we estimate and approximate a standard lead time based on normal operations, we need to set it with a certain margin. Here is the formula for safety stock. It is expressed as safety stock equals average daily demand shipment times safety days. For example, if the average daily shipment is 10 units and the safety days are 3 days, the safety stock is 30 units. In principle, these 30 units are the minimum inventory to be held and are not used unless an unexpected event occurs. Next is the calculation of the reorder point. The reorder point is the threshold at which an order is triggered when inventory falls below this number. The reorder point is the sum of the inventory consumed during lead time and the safety stock. The inventory consumed during lead time is calculated by multiplying the average daily shipment by the procurement lead time. For example, assuming average daily shipment is 10, procurement lead time is 5 days, and the safety days is 3 days. The safety stock is 30 units. The consumption during lead time is 50 units. Therefore, the reorder point is 80 units. We need to place an order when the stock drops below 80. This is an image of the reorder point. The vertical axis is inventory count, and the horizontal axis is date. With daily shipments, inventory gradually decreases. When the inventory touches the reorder point line, the system places an order. Since there is a procurement lead time, the goods do not arrive immediately even after ordering. Inventory continues to decrease by a certain amount. At the timing when inventory reaches the safety stock level, the ordered goods arrive. The ordering method introduced here is a method where a fixed order quantity is defined in advance. Generally, this is called the fixed order quantity system. An order is placed when the inventory level falls below the reorder point. On the other hand, a method where orders are placed at predetermined intervals is called the fixed order interval system or periodic review system. In reality, there are many more ordering methods. Also, depending on the industry and items, ordering is done based on specific know-how. For example, even in automotive parts, materials such as iron, resin, and lithium have different shelf lives, expiration dates, so it is common to define ordering methods individually. Next, just as we have done before, we will add the reorder point and the safety stock logic we just explained to our Python code. We will finalize the Inventory Manager class by adding the last remaining features, logic 6 and 7, to the code we built in the previous sessions. First, we will modify the initialization method to accept new parameters. Also, we will ensure that safety stock and the reorder point are automatically calculated the moment the class is instantiated. Next, we will modify the ship order method. We will add an alert function to automatically check has it dropped below the reorder point immediately after the outbound process, reducing inventory. As a side note, receive stock and reserve order do not require any changes in this section. First, we extend the initialization method to add ordering parameters. When initializing the class, we receive all necessary calculation parameters and save them to self. The init arguments have now increased to 5, while logical stock and the reserved stock represent the state. ABG, daily, demand, and others are parameters for calculation. Continuing with the initialization method, here we write the expression to save the state parameters. Next is the automatic calculation of safety stock and the reorder point. Once init receives the parameters, it calculates the safety stock and the reorder point at that moment. To keep init clean, we extract the calculation logic into separate private methods. Inside init, we add the expression self.safety stock equals and self.reorder point equals. Here are the content of the private calculation methods. Now, the moment Inventory Manager is created, the calculation results are automatically populated into the self.safety stock and self.reorder point variable properties. The formulas are exactly as we learned in the previous lecture. For reference, math.ceil after the return statement is a function that rounds up decimal places. In inventory calculation, it is standard to round up to stay on the safe side rather than using fractional numbers. Next, we add the alert function to ship upon order. This reflects logic 7. We need to detect the moment the inventory drops below the reorder point. The timing when inventory decreases is immediately after outbound processing. Therefore, we execute this in ship order where the outbound calculation is performed. Here is the added functionality. After reducing the inventory in ship order, we added the process if self and a check reorder checkpoint. The check reorder point is a newly created helper method which performs a simple comparison. Self, the logical stock less than or equal to self, reorder a point. If it returns true, meaning it dropped below the reorder point, we output a log with the print and append an alert string to the return message. Ordering is based on how much the total warehouse inventory has decreased. Even if available inventory becomes 0, it just means there is nothing to sell right now. Physical stock might still exist in the warehouse. Therefore, we consider ordering only when the logical inventory decreases. This completes the Inventory Manager class. Next, we will execute unit tests to verify if the calculations are correct. Next, we will deploy the Python code we just discussed to Lambda and execute unit tests. First, let me outline the unit test plan. In this unit test, we will define 2 scenarios to verify whether automatic calculation is performed correctly and whether the reorder point alert functions correctly. First is the verification of automatic calculation. We will confirm if safety stock and the reorder point are calculated correctly upon the initialization of Inventory Manager. Assume the current logical inventory is 100, the reserved inventory is 10, average daily demand is 10, lead time is 5 days, and the safety days is 3 days. When we execute the test, we expect the safety stock to be 30 and the reorder point to be 80. In the second test, we will verify that an alert is triggered the moment the inventory drops below the reorder point as a result of shipping. With a reorder point of 80, we will ship 11 items from a logical inventory of 90, bringing the inventory down to 79. Since it dropped below the reorder point, we expect an alert message to be appended. We will now proceed with the hands-on session for the section 4. So, as we did in the previous section, and we will deploy the code and performance test from the Stock Manager Lambda function page in Lambda. So just like before, and copy and paste the Python code into the code tab and deploy it. And this calculation inside as what was explained in the lecture. And when we have added the 5 argument to the Lambda event handler function to actually receive the event from the outside and perform the calculation, logical stock, reserved stock, the average daily demand, and the lead time days and safety stock. So with this state, I'm gonna deploy. Okay, the deployment should update immediately. So now click on the testing tab, and from here we will execute 2 types of the test on the same way as before. So scrolling down and clicking on the create a new the event. So the first test is named the test ROP calculation, and we will verify if the safety stock and the reorder points are calculated correctly. So scrolling down to the event JSON, and I'm going to paste the JSON, and the action is a check init, and the quantity is 0, the logical stock is 100, and the reserved stock is 10. The average daily demand is 10. The lead time days is 5, and the safety stock is 3. And we will confirm only if the calculation is performed correctly based on these values. So going up and clicking on the save and execute the test. So looking at the result, and so I'm going to see the auto calculation result. The safety stock is the 30 and the reorder point is 80, and this confirms the calculation is correct. So the next verify if the reorder point alert is triggered correctly, and on the same way clicking on the create new event and name it this time the test SIP trigger ROP, and paste the JSON here. So set the action to SIP, and the meaning outbound shipping, and set the quantity to 11, and set the current logical stock to 90. With the current logical inventory at 90, the reorder point is calculated as the 80, subtracting the 11 from the 90, resulting in the logical inventory of the 75. And since this falls below the reorder point, we expect the alert message to be displayed. So save and executing the test. Okay, the test result appear very immediately. So as I explained, it says okay, the final message, the alert message is shown here. The drop below the ROP is 80, and the current is the 79. This confirms the calculation and the alert are displayed very correctly. So this concludes the unit test for the scenario 4, and we have completed all the unit tests throughout the section so far. However, in the unit test up to this point, we just input the JSON data directly within the test tab. So from the next section, and we will proceed to the integration testing and inputting the test data here, and we will input the actual data from API gateway and check the results. Next is section 5, the business scenario testing with API gateway integration. In this section, we will integrate the individual function developed in the previous sections and execute scenario tests as a single unified system. In the previous sections, we completed the Lambda and the DynamoDB components. However, we do not have an API gateway yet. Also, the Lambda function is currently in a state where we are just manually passing JSON data to invoke it, and we will integrate all the components created so far to complete it as a single system. Amazon API Gateway is an interface service used for web application. It receives requests from the outside and routes them to other services. Conversely, it sends the responses from internal AWS services. In short, it acts as the front door for integrating with external services. Using API Gateway allows for easy creation and management of APIs. Also, since it is a fully managed service, users do not need to manage scaling even if the request volume increases or decreases. API Gateway supports HTTP APIs, REST APIs, and WebSocket APIs. As a serverless service, it primarily integrates with Lambda to forward requests sent to the API Gateway to resources within AWS. Let me introduce the definition of an API. API, Application Programming Interface, refers to a mechanism that exposes a part of an application to the outside, allowing it to be shared with third-party applications. Interface means a point of interaction or a boundary. For example, a user interface refers to the point of interaction between a user and a computer, such as a web browser or operation tools. Using APIs eliminates the need to develop application from scratch, leading to development efficiency and cost reduction. Along with API, I will also introduce the term REST. REST is a design principle suitable for coordinating multiple software components in distributed systems. It possesses the characteristics listed here. API Gateway supports not only HTTP APIs, but also REST APIs. Here are the APIs we will create this time. We will create 3 types of APIs: inbound, order allocation, and outbound. We assume that external users will execute these 3 types of requests against the system. Additionally, API Gateway has a native feature called the Lambda proxy integration. This allows API Gateway to pass the received request information as is to the Lambda event object. This enables the Lambda function to easily grasp the entire content of the request. So, we are going to create an API gateway. As usual, I am on the top of the page of the management console, and if you type the API gateway in the search bar, and you can navigate to the API gateway's service page. So from here, you can create a new API, and you will find the Create API button on the left menu bar or on the main page if you are in the initial state. I'm going to click on the Create an API. So, and here you will select the API's type. You can choose from the HTTP, WebSocket, REST API. And this time we will choose the REST API. And by the way, there is also REST API private option for private feature within the AWS Virtual Private Network. But since we will be accessing this from the outside via the internet, and we will click on the build on the regular REST API. So since we are creating the new API, select the new API, and we will name it the inventory API. So for the API endpoint type, you can choose the regional, the edge optimized or private, but this time we will select the regional. And by the way, as I have mentioned several times in the previous hands-on session, that I am consistently creating the all resources in the US East, the North Virginia region, US East 1. So this is a relatively new feature. You need to choose the security policy from here. And I'm going to choose the security policy with the TLS 1.2. And this is used for the encryption for the transportation. So scrolling down to click on the Create API. Since this is also a serverless service, it should be created successfully and immediately. So now let's actually create the resources. And the UI for the API gateway has changed several times in the past, but we will create using the current UI. So clicking on the Create Resource from the Resources menu on the left menu bar, and make sure the root slash is selected and first enter the receive. I'm going to choose enter the receive, the resource name receive, clicking on the create the resource. So you can see the receive has been created under the slash. So next select the slash again and create the reserve next time in the same way. I'm going to copy and paste the reserve. So enter the reserve and click on the create a resource. Then you can see that the reserve is placed under the slash. So click the slash and one more time and create the resource. And this time enter the zip and meaning outbound as the resource name. So clicking on the create a resource. So now the zip is created. And we can see that the three resources, the receive, reserved, and the zip have been created. So next going into the receive resource, and we will configure the method and the Lambda proxy integration. And with the receive selected, clicking on the create method. And you can create the method from here. For the method type, select the post method, and with post selected, choose the integration type. And there are several options, but since we are using the integrating with the Lambda function, so select the Lambda function. And as explained in the lecture, verify that the Lambda proxy integration is the toggle of the on, and check the box and scrolling down. And since I am in the North Virginia, so choose the US East 1 and choose the Lambda function we've created, named the Stock Manager Lambda, and leave the other parts as default and create the method. You can see the post has been created under the receive. So similarly for the reserve, using the exact same method, select the method type post and choose the Lambda function and enable the Lambda proxy integration and select the Stock Manager Lambda in the US East 1 and create the method with default setting. And this should also be done very quickly. And finally do the same for the zip. Click on the create the resource and create a method. Choose the post method type. Integration type is equal to Lambda function enable the Lambda proxy integration and choose the stock manager Lambda. Okay, and scrolling down to click on the create method. Okay, confirm that the post method have been created under receive, reserve, and save. And finally, we will deploy API and retrieve the public URL. And there is the deploy API button at the top right. And it might take a few minutes for this deploy API button to be enabled. So clicking on the deploy API and select the new stage for the deployment. This time I'm going to name the DEV representing the deployment development and clicking on the deploy. And soon you will get the invoke URL here, and we will be sending the request to this URL later chapter. So this concludes the explanation for creating the API's gateway. Next, we will integrate Lambda and DynamoDB. In the previous sections, we completed the API gateway, Lambda, and the DynamoDB components. We also executed the unit tests and verified that each function operates correctly. From here, we will combine all the components built so far to complete it as a single unified system. Up until the previous section, we were manually inputting JSON sample data for unit tests and verifying the results using the test feature in the Lambda console. This time, we need to pass the data from API gateway to Lambda and write the results to DynamoDB. Specifically, inside the Lambda function, we will pass the event sent from API gateway and identify the product underscore ID. We will also retrieve the inventory data existing in DynamoDB. Once the Lambda function acquires the necessary information from API gateway and DynamoDB, it performs a calculation using the inventory manager. Then it writes back the new inventory counts to DynamoDB. Furthermore, it returns a response, success or failure to API gateway. At this stage, we will also grant permission for Lambda to access DynamoDB. Lambda reads the inventory data from and writes data to DynamoDB. For this, read and write permissions are required. In AWS, we manage these permissions using a service called IAM. Let me introduce IAM. IAM, Identity and Access Management, is a service that manages access permissions to resources and the accounts that access them. Using IAM allows for fine-grained access control, defining who can perform what action on which service. This enhances the security across the entire environment. As mentioned during account creation, a root user is created initially, but typically you sign in as an IAM user. An IAM user holds permissions to execute specific actions on specific resources. Furthermore, IAM can set permission not only for users, but also for resources. For example, you can set permissions to allow a specific Lambda function to execute or be restricted from specific actions on a specific DynamoDB table. This enables security designs such as the principle of least privilege. Next, I will introduce the final Python code. And since it is a bit long, I will explain it directly from the editor. And first, regarding the import at the top and the bottom 3, and this is a Python library used to operate AWS services, and we are importing this. And the next, regarding the import decimal, and DynamoDB uses a special numerical type called decimal, and we import this to maintain the compatibility with the Python integer type we have been using so far. The rest of the logic is exactly as I have introduced previously, and however, scrolling down to the Lambda handler. In the unit test so far, and we retrieve the data directly from the JSON, but this time we will input the data from the API, specifically from the API gateway. And here, we have the conditional branching to determine which API was called, the receive, resolve, and SIP. And scrolling down to the bottom, and here we have added the logic to retrieve inventory data from DynamoDB and write the data back to it. And previously in unit test, we input the JSON data directly from the Lambda test tab. And however, for this final integration test, the flow involved retrieving the inventory data from the DynamoDB table and updating it and then writing it back. So therefore, we have modified the logic within the Lambda handler function accordingly. So let's proceed with the final configuration. I'm going to the Lambda service page and clicking on the stock manager. The firstly, and clicking on the code tab and open the code source and scrolling down to the Python code and paste the Python code directory here. So clicking on the deploy, and as before, the deployment should be the update immediately. So next we will configure the settings like to this Lambda function to access the DynamoDB table. Clicking on the inside the configuration tab, and from the left menu bar select the permission. And here you will see the IAM execution role. The IAM role is created with the naming conventions like stock manager lambda role with the random string, and combine the function name, you create the random string. So if you click on this role name and so going to the IAM roles page. So here we will add the permission to allow access to the DynamoDB. Under the permission tab, and there is the add permission, and click on the attach policy. And as you see, there are currently over 1,000 IAM policy listed here. And since we want to grant access to the DynamoDB, so type DynamoDB in the search bar, and you will see the Amazon DynamoDB for access. And this policy defines the full access permission for the DynamoDB, and we will use this one for this time. And strictly speaking, we don't need full access permission, and usually the specific permissions like write or update would suffice, and the least previous principle. However, since this is just a hands-on tutorial, and we will select the full access policy, and check the box to select it and click on the add permission. So you should see the message indicating that the policy has been successfully attached to the role. And now you can see the Amazon DynamoDB for access has been added to the permission policy under the stock manager's role. So this concludes the explanation. Next, we will proceed to execute the integration tests. In the previous lectures, we completed the entire system. In integration testing, we will verify if requests sent via API gateway trigger processing in Lambda and are correctly reflected in the DynamoDB table. We will use an external tool to execute requests to API gateway. Here, we will use an API testing tool called Postman to simulate real-world business scenarios and test if the system operates as expected. Postman is a tool for sending API requests, checking responses, and creating mock APIs. It supports API development. Currently, there are web and desktop versions, but we will use the web version, which can be used directly in the browser. If you search for Postman on Google, you will find their homepage. The layout may change, but usually there is a sign up or sign in button at the top right. You can sign up for Postman using your email address, Google account, or GitHub account. Postman offers multiple paid plans, but since this is a simple demo, we will use the free version. Let's explain the content of the integration test. First, ensures the DynamoDB table is set with the logical stock at 100 and reserved stock at 0. You should have already entered these initial values during the hands-on session in section 1. From here, we will actually execute requests using Postman. First, we assume receiving an order for 30 items. We will call post/reserve to accept an order of 30 and verify that reserved stock increases by 30. We will verify if the inventory actually increased by checking the response message returned to Postman and by directly checking the DynamoDB table. Next, we will ship the 30 allocated items. We execute post/ship to ship the 30 items allocated earlier from the warehouse. We verify that both logical stock and the reserved stock decrease. Again, we verify the results via the Postman response message and the DynamoDB table. Finally, we will trigger the reorder point alert. We will repeat shipments until inventory drops below the reorder point and verify that an alert is returned. The parameters for product A-001 are ABOK daily demand equals 10, later time days equals 5, and safety days equals 3, so the reorder point automatically calculated by Lambda is 80. The current logical stock is 70, so it is already below the reorder point. Therefore, the alert should trigger on the next shipment. First, we call post/reserve, set QTY in the body to 1. As a result, reserved stock becomes 1. Next, we ship that single item using post/ship. Then, Postman will display an alert message indicating that we have dropped below the reorder point. By verifying this sequence of flows, we confirm that the entire system operates correctly. So let's proceed with executing the final integration test. And we will be using the Postman and DynamoDB, and you will have the multiple browser tabs open, switching between the API gateway, Postman, and the DynamoDB table page. And first, I will go to the API gateway dev stage, and that we created in the previous section, and copy the invoke URL. And now switch to the Postman page, and in Postman create a new request, and there is a field to paste the URL. And since the request method this time is post, and select the post, and in the tabs below select the body, and then select the row, and ensure the JSON is selected. And here we will input the actual JSON code, and we will send it to the later. So before doing that, let's open the DynamoDB table, and from the DynamoDB table, open the product stock, and let's check the initial state of the table item. Clicking on the Explore the table item, and for the product ID, the A001, the average daily demand is 10, and the lead time day is 5, and the logical stock at initial state is 100, and the reserved stock is 0, and the safety stock is 3. So this is the initial configuration, and confirm that this is set. So we will verify the contents between the Postman and the DynamoDB table. First, let's perform the reserved, the order allocation. To perform the reserve, we need to append the slash reserve and to the URL. So, and the next inputs the JSON in the body with the product ID is the A001 and sets the quantity to 30. So clicking on the send. Okay, immediately you will see the order success allocated at the bottom, indicating the allocation was successful. So now let's confirm the evidence switch to the DynamoDB. So the request was sent from the API gateway, processed by Lambda, and the results should be in the DynamoDB table. So currently, the logical stock is 100 and the reserved stock is 0. And if I refresh this item, okay, logical stock remains 100 and the reserved stock, the allocated inventory, has become the 30. And this is the flow of allocation. The physical inventory is in the warehouse 100 hasn't changed yet, but the 30 items have been allocated. Although not explicitly stored in the table, we can reduce the available inventory is now 100 minus 30 and it's 70. So next let's execute the post for the SIP. Okay, then going back to the Postman, then we will execute the SIP and change the endpoint URL from the reserved from the SIP, or open the new tab in Postman and okay, copy and paste the URL to the new tab and change the post and change the /c SIP and in the body tab, I'm going to copy the same JSON format into the body. Okay, it's using the same quantity 30, and we will now perform the SIP. Okay, the response returned very immediately and the shipping success. The local inventory is 70 and the reserved stock is 0. So again, let's check the DynamoDB table again. And before refresh, the logical, the 100, reserved 30, and after refresh, the logical stock is the 70, and the reserved stock is 0. And this confirms the outbound processing. So finally, let's execute the reorder point alert. Okay, going back to the same page and to make sure it's post and first change a URL to reserved. Okay, and in the body set the quantity to this time to 1 and click on the send. Okay, the result is logical inventory is 70 and the reserved stock is 1. And now perform the SIP again and click on the send. Okay, the reorder point is 80, the calculated previously. The logical inventory is changed to 69. So we have the alert message because it's already below the reorder point. So The shipping success, but logical inventory becomes the 69, and it means the drop below ROP, the 80, and we can see the alert is returned. So this completes the integration test that we simulate the all business scenario. The API gateway receives the request via the postman, and the Lambda reads the DynamoDB data, and the inventory manager class executes the allocation and the reorder point logic, and the Lambda updates the DynamoDB data. So as a final check, looking at the DynamoDB table again, and refresh, and as you see, the logical stock becomes 69. Okay, this proves that the entire system flow operates correctly, and this concludes all hands-on sessions. Finally, we have the summary and an introduction to the advanced features. In this section, we'll recap what we have learned so far and introduce the concept of historical data retention as an advanced topic. As a summary, let's review the course objectives. First, we learned the essential logic for inventory management, such as available inventory and reorder points. We didn't just write code, we learned the underlying domain knowledge together, and next we wrote code using Python classes on Lambda. We also practiced the full development cycle, development, unit testing, and integration testing. Finally, we built APIs using key serverless services, API Gateway, Lambda, and DynamoDB. In Python, we structured the classes and developed 7 logic components as functions. These classes are executed in the appropriate sequence according to the API execution timing. This ensures the integrity of both logical inventory and allocated inventory. We also learned about the roles of basic AWS services. It is not enough to simply use AWS services. You must understand the business challenges of inventory management and select the optimal services to solve them. From here, we will explore some advanced topics. With the system we have developed so far, we cannot check inventory history at a specific point in the past. This is because Lambda overrides the data in the DynamoDB table each time. In the next lecture, as an advanced topic, I will introduce features for preserving past history